Well, now I turn to introducing someone who needs no introduction, but it's my job to introduce John Hennessy. John is a professor of electrical engineering and computer science. He served as Stanford's Dean of Engineering, then Provost, and then began his amazing run as Stanford's president. That was from September 2000 through August 2016. He barely caught his breath. In 2017, he initiated the Knight-Hennessy Graduate Scholars Program, which has now welcomed 2 cohorts onto campus, and these are remarkable scholars across all fields of the university. That same year, John won the Turing Award together with David Patterson. Many of you probably know that the Turing Award is widely considered the computing equivalent of the Nobel Prize. And Hennessy and Patterson were cited, quote, for pioneering a systematic quantitative approach to the design and evaluation of computer architectures with enduring impact on the microprocessor industry. Winding back 30 years, though, before that, John's first leadership role at Stanford, I believe, was as the director of the Computer Systems Laboratory. And CSL was established as a research and teaching center jointly between the departments of electrical engineering and computer science. And the CSL itself, I would say, laid the groundwork for a great relationship between EE and CS that remains to this day. And I would just say that's one of John's many, many legacies. So please join me in welcoming John.
Actually, I should say one of my really great legacies was that we hired Jennifer Widom to join us here at Stanford. So if you were to open up the newspaper and read all the stories about the end of Moore's law, you'd conclude the sky is falling. The sky is falling. Instead, I prefer a quote by Alexander Graham Bell, who once said, when one door closes, another opens. So what I'm going to show you that, in fact, one door is closing, and give you some brief insight into that, and then show you how we can rethink about how we use semiconductor technology and how we do computing to open up other doors. So here's a classic plot of what's happened in microprocessors over a long period of time. You look at that incredible era from the mid-'80s to around 2000, where you're yielding 50% a year of performance improvement. The software guys just stand there, and the hardware guys do all the work, and boom, 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 computers get faster automatically. It was a really wonderful period. Then a period that was pretty good, 20-something% a year. Then a beginning slow down. The last few years, almost nothing. And if you saw these plots everywhere, you'd see the end of Moore's law as the blame. Poor Gordon, I think he gets blamed for this after, as he said, it wasn't a law, and all exponentials end sometime. All exponentials end sometime. In fact, if you look at how we're doing, we're only about a factor of 10 off of an extrapolation of Gordon's 1975 prediction. Only about a factor of 10, while we've gained about a factor of 1 million. 10 out of 1 million. That's a small amount that we're off. Now, the gap is clearly getting bigger. Clearly, there's a slowdown occurring, but it's not the key driving force. The key driving force is the failure of DENNARD scaling. Bob Dennard made this incredible observation that as we scaled things down, the power per square millimeter would stay constant. If the power per square millimeter stays constant, but I'm getting quadratically increasing numbers of transistors, then I'm getting more transistors for the same power. Or another way to look at it is computing is getting more and more energy cheap, right? Because I can get more done with those transistors. And you begin to really see that take off sort of shortly after 2000, but then really since 2007. And that's the real problem. And of course, it's compounded by the fact that we care a lot more about energy consumption. After all, the most important computer everyone carries is in their pocket, right? And we care a lot about the energy consumption of that device. Obviously, with IoT and a much more mobile world, we care about it there. But turns out in the data center, The second most costly part of the data center is the electrical and cooling infrastructure. And of course, the energy that you need to continue to cool those machines and run the computers. So it's follows right after servers in terms of its cost impact. We've also maxed out on thermal dissipation, and not only would you worry about battery life, you also don't want something that's going to leave a burn mark on your thigh when you put it in your pants, right? So we've got all those kinds of issues to worry about as well. The problem is the techniques we've been using for the past 30 years in computer architecture have hit a wall with respect to their energy scaling. Let's just take one simple example that's easy to understand. Think about what have most of the transistors gone to in the last 30 or 40 years in microprocessors? They've gone to build caches. Level 1, level 2, level 3 caches, more and more caches. Think about a cache. The bigger the cache gets, at least the static power scales linearly with the cache size, and the dynamic power in some strange way, some partly proportional to it. But the cache, of course, as it gets bigger and bigger, you use less and less of it. That's the whole reason that programs have locality. So you basically have a diminishing returns situation. Whoop, wrong button. And in fact, we also have that on the primary technique that we use to make machines to make single processors fast, right? This technique called speculation. We try to predict which way the program will go. We run down that path. We bring in instructions. In a modern Intel i7, there are well over 100 instructions that are being operated on at any given time. Over 100. So all that, we're trying to extract all that parallelism and find all kinds of opportunities to make it run fast. The problem is that, of course, we don't guess perfectly right. We have great branch prediction techniques, all kinds of things. We try to guess which way the program is going to go. But when we're wrong, all the work we did, fetching those instructions, executing them, dispatching them, doing all the control, was wasted. All gets thrown out. Not only do I throw out and waste all the energy associated with it, but by the way, I also take some more time and energy to get the machine back to where it was, where I know I'm in the right state and I can begin executing down the other path, the one I didn't predict. So you throw away a lot of work. That basically is the thing that ended the kind of uniprocessor path. So everybody said, well, since the hardware can't do anymore, let's let the software people have the problem. And they said, let's switch to multicore. And what multicore is a little bait and switch. It says, well, we hardware guys don't know what to do, so we'll ask the software people to identify all the parallelism and let them worry about it. The problem with that multicore era is that the energy is proportional to the number of transistors you're switching, which is proportional to the number of cores you have active. Right? And if you want to see how hard this problem has gotten, who would have guessed 30 years ago that we'd have multi-core processors and the cores would turn themselves off to prevent chips from burning up? I never thought we'd get there. But of course, it happens all the time now. All the time. And of course, as Gene Amdahl observed many, many years ago, Amdahl's law is still with us, which basically says anything you do parallel is limited by the portions of the computation that are sequential. And if you add that kind of always gives you these kind of asymptotic curves. But now you have to consider something else. You have to consider the energy limit. How much power can you suck out of that chip? When you consider that, you get these curves that flatten over, because even when you get the program running at maximal parallelism, you can't run it very long like that before you burn the chip up. So now you could say, well, we can suck more heat out of that chip. We can. And then we'll all be walking around with fins on our back so that our cell phone doesn't burn up, right? It's a difficult problem. So where's the opportunity? Well, think about what's happened in the last 30 years to all that performance, all that computer power. Well, the software people used it to try to improve productivity of software. Well, that was a pretty clever use. If hardware is continuing to deliver more and more performance, using it to boost software productivity was a good use. And we moved to modern scripting languages that are interpreted. Everybody writes in Python. But we pay an enormous performance penalty. And this is from a little experiment that a group of colleagues at MIT did, where they took matrix multiply, admittedly a simple application, one that can be highly optimized, and they wrote it in Python. Then they rewrote it in C. It ran 47 times faster than the Python version, 47 times. Now, by the way, before I did architecture, I was a compiler person. Compiler people kill for factors of 2. Factor of 47, gigantic. Then they introduced parallel loops. They get another big factor out of that, 30 out of that. Then they introduced memory optimization, using the memory structure right and laying out things properly so that the caches were effective. They get another factor from that. And then finally, they use the vector instructions in the Intel architecture. The final program runs 62,000 times faster. 62,000 times. That's where a lot of the performance went. That's a hard problem to do that, but certainly one worth thinking about. There's a build slide in here. There we go, 63,000 times faster. What about rethinking architecture? Well, the way to rethink architecture is to say, can we do something that's more domain specific? That is, rather than try to do everything in a general purpose way, focus your attention on applications where you can exploit particular behaviors of the application. In order to get that to work, we're also going to need to think about different programming models, because I'm not going to take Python or C and really use these kinds of architectures efficiently. I'm going to have something that conveys higher level information that enables me to exploit it in the hardware. Now, in the past, most attempts to move to the special purpose space have been crushed by the relentless progress of general purpose processors. Lots of companies have built special purpose hardware. They get out there, they last a few years because they were initially ahead, and then the incredible progress of general purpose processors, plus their tremendous cost advantages when you can ship them to a large market, crush it. So why is this time different? Well, we have one example where it's clearly different. GPUs are a great example. Graphics processors are special purpose, domain specific for graphics, and they've been tremendously successful. So A, it will be different because there is no great story for general purpose processors anymore. And B, it'll be different because we're going to exploit the kind of information that, for example, gets exploited in a GPU, and we're going to tailor something that has sufficient flexibility that we can do a domain of applications. So how do we think about these domain-specific? They're programmable processors. We're not talking about a modem, for example, that is, in fact, programmed but doesn't do any other function. We're talking about a processor that is Turing complete and can run full programs, but does a certain set of things really well. And that's a class of applications. If we can take advantage of the structure, we can get incredible performance. So let's just take a quick look and see can we get some insight where the opportunities might be. And this is some data that originally Mark Horowitz assembled most of it, but it just gives you an idea of the amount of energy used for various functions. When we think of computing, we think a lot about adds and multiplies and things like that. Look how energy cheap adds and multiplies are. That's not where we're spending all our power. We're spending on things like control, right? Decoding instructions, figuring out what to do next. We're spending it going off chip to get to DRAM. Even accessing caches, we're spending a fair amount of power compared to that. So we have to rethink how we shift the computational function to favor the kinds of computations that will be more energy efficient. If you take those numbers and you put them together for an instruction on a typical Skylake i7 type processor, what you'd see is something like this. The vast majority of the energy is being devoted to doing the control function. A bunch to L1 cache access. That's just instruction cache access, is getting instruction. A bunch to that, and only a very small amount to the floating point multiply. Can't we do better? Can't we rethink what we do? So that's a key insight behind why domain-specific architectures can work. We can't just say, we're going to go to something that has a more limited domain, and it's going to be great no matter what. We have to clearly articulate what the advantages are. So shifting the mechanism for getting parallelism out from multiple instruction, multiple data to single instruction, multiple data. So we're only fetching one instruction and doing many operations from that one instruction. Changing the model of how we exploit parallelism within a pipeline. Trying to think about how we can get the user, by coding at a different level, to really give us key information about how to use memory rather than take caches, which are a very general mechanism, but not particularly efficient, and particularly not efficient for whole classes of applications. We can think about using lower precision rather than full IEEE as a way to get performance. All those will win. What about application space? While Moore's law may be slowing down, the rate at which papers in machine learning are getting published exceeds Moore's law. So we have an application space that people really seem to like, that continues to grow and grow. And you should think about this as programming with data, because that's really what's happening. And it's growing very fast, and it is intensely computationally intensive. So how do we think differently? So here I just took the TPU-1, which is Google's first TensorFlow processor. It's an inference-only processor, but just to give you an idea of how silicon gets used in a processor like that versus a standard general-purpose CPU. And you notice there's actually more of the space is getting used for memory, more of it for compute, and a lot less for control. So that's the big shift. We're using it for something which is much more germane to the application that we're trying to do. The other thing we do is try to shift how the computation works. So if you think back to that slide where I showed you how much energy is being consumed for various things, what you'd love to do is do more arithmetic and less memory access. So you try to shift the application in that direction. And that's what these roofline plots show. So this plots on the x-axis how computationally intensive is something. That is, how many arithmetic operations do I get to do per piece of data that I bring from memory, versus what the throughput of the machine will be. So if you see what happens on something like a TPU, what it does, it really benefits when I can shift the arithmetic intensity so that there's a lot more computation per memory reference. We also have to rethink how we think about computing. We never think about the question of, is it cheaper to recompute something or compute it twice than it is to communicate it? And the answer is often it's cheaper to recompute it. But that means we have to rethink how our compiler systems work and how our software systems work if we're going to realize that. So there's a gigantic compute demand here, because while inference is moderately compute intensive, training is extremely compute intensive. And just to show you, look at this curve of, this is from AlphaGo 0, which is the DeepMind chess playing program that plays chess starting from ground zero, no knowledge of any strategies in chess, and now is the world champion. And all the way in the end, some early machine learning programs. Basically, that AlphaGo training time is roughly equal to 24 hours on the world's largest supercomputer. So that's a fair amount of training time. So there's a computation that you'd really like to run fast. So you can build processors to do that. By the way, when you move to this space where you're thinking about your interface, not in a traditional instruction set architecture mechanism, but a higher level interface, a domain-specific language becomes your interface, it means that subsequent generations of architectures don't have to be compatible in the same way that they do in the general purpose space. So you can innovate more, you can reduce the verification time, because it's much easier to verify these machines if they don't have these complex instruction sets that have evolved over a long period of time. So there's a lot of advantages in terms of how quickly you can introduce new architectures and tailor them to specific domains. And you can even build these into massive supercomputers if you want, and basically gang them together to build these pods that are massive amounts of computing power. And if you, the one based on the third generation is over 100 petaflops peak. And if you compare it to the largest computers in the world, they look pretty good. They're somewhere between 25 and a half as fast as the largest computers in the world. They cost a small fraction of it. But they're also very efficient. If you look at the bars in green, they're very efficient in terms of energy use. So that becomes critical, particularly as machine learning and things move out to the edge of the net and you start to use it everywhere, then the energy effectiveness becomes even more important. So I like to think about this as a series of challenges and opportunities, and I think there are a lot of opportunities for electrical engineering here. EE has always been a discipline that spanned from applications to fundamental technology. And this is an opportunity to make progress by being able to span across that, by having Renaissance researchers who can actually communicate across through that vertical stack to really do something interesting. So thinking about how we optimize these architectures and we build languages to efficiently program them. Thinking about how we make hardware design a lot easier. If we're going to build machines targeted to individual niches in the application space, we have to figure out how to make the design of those much cheaper than it is today. We need to make hardware design as easy as software design is. Now, software guys have a big advantage. They release a piece of software, it doesn't work so well, they release a bug fix. Bug fixes are a lot harder in hardware, but that doesn't mean we couldn't begin to think about designing machines that could somehow be patched in the field somehow by a software fix of some sort. Particularly if we move the abstraction level that we have to interface to up a little bit, then our life will be easier. And of course, if my friends on the technology side make a great breakthrough, whether in quantum or carbon nanfiber or figure out how to punch a hole through Moore's law and DENNARD scaling, we would be very grateful if you would do that. That would make our life a lot easier. But we'll find other ways to do exciting things. I love this quote by Dave Cook, who worked on the Iliac 4, one of the early SIMD machines. And he said the problem was we didn't have enough software people. In fact, he was the software architect. They had lots of hardware architects, but they had one software architect, with the result that they built a machine that people found impossible to use. What we have to do is merge that and span those opportunities. I like to think of a great quote by John Gardner. What we have before us are some incredible opportunities disguised as formidable challenges. Thank you. I think I didn't go too long. I think we have a few minutes for questions. Kevin.
Is it the purpose of faster hardware so you can make software programming?
Yeah, so I have no objection to the fact that we use that way. In fact, I think it's a great idea that we used a faster hardware to make programming easier. Now the question is, could we get some of that inefficiency back somehow by some clever work on the software side? There's nothing wrong with using it to make programming easier, for sure. I mean, we wouldn't have produced all the code we've produced in the world and have all the great applications we have. So, yeah, absolutely. I can't see because of the lights.
Who are some of the young researchers that you like? Who are some of the young researchers that you like that are looking at these areas?
Oh, well, there's some people here at Stanford looking at it. Kunle Coton, Bill Daly have all looked at some of these problems and done interesting things in it. We have a new faculty member coming in the spring who's worked on a particular problem. And one of the really hard problems in this space is what do you do about sparse codes? Big deep neural networks are actually highly sparse matrices. So figuring out how you deal with that in an effective way is an important problem. So we have people working on that. There's a lot of activity, but I think it's a time when university research can play an incredible role, because you've got to span this vertical stack, and it's going to require some really hard thinking. Industry's moving very fast, they're doing great things, but maybe universities can play a unique role by thinking deeply about these problems and how to do something that's dramatically different.
What is your opinion of AI optical processors?
I don't have any objection against optical as soon as somebody shows me something that it's just like quantum. I'm waiting. So I don't have any objection against optical. I mean, if it provides better opportunity. Clearly, communication costs are cheaper in optical if the distance is long enough. You've got to compare that against an approach, which what I'll try and do in silicon is make all the distances short, right? I'll try to avoid communication by shifting the way I do my computation. So there are two different ways to attack that problem, I think.
I have a question, sorry, about this domain-specific architectures that you recommend. Wouldn't that make the task of programming even more difficult for people who are actually entering this business? I attended a recent thing in medical. I mean, there are doctors who are actually starting to program and write AI code and all that.
So the answer is, to some extent. The advantage of general purpose processors, for the most part, people threw their code on it and it worked pretty well most of the time. Not all the time, right? If you put a big linear algebra code on a conventional processor without understanding how caches work and various other things, it doesn't work very well. I think what's going to happen is we're going to have to shift the level of our programming paradigm. So stop writing. I mean, what do we write in a little better than, it's a little better than assembly language, but not that much better. Shift it up, go up to a domain-specific language, shift up, talk about what your code looks like. If you're writing code that's dealing with matrices, write about matrices. Write about matrix operations. Don't write about loops that decode it down into individual array accesses where I can't recover the high-level structure and can't do something really clever. So that's what we have to do. That'll balance some of the difficulty in programming. It is the case that performance will be much harder to predict in this space than it was for general purpose processors. That is certainly the case. And since we all care about performance, it's a critical factor. Tom.
Yeah, not a question, just to supplement your closing remark with a quote from by a famous American philosopher, Yogi Berra, who said, "We're surrounded by insurmountable opportunities."
Insurmountable opportunities. I like it. I thought he said, when you come to a fork in the road, take it. Okay, thank you.